Mathematicians have been interested in area minimizing surfaces and surfaces of constant mean curvature for several hundred years. These surfaces are of pure mathematical interest in both geometry and partial differential equations and arise in a number of applied fields. In this video, we're going to try to describe the basic theory of minimal surfaces, tell you about some of the more recent developments that include construction of surfaces and theories to try to explain why examples exist and why some examples don't exist, and finish up discussing surfaces of constant mean curvature and their application in current-day research in polymer physics. We're going to begin by defining the curvature of a plane curve. Here we have drawn at 2 points of the curve the circle that makes second-order contact at those points. In other words, it is tangent and its second derivative agrees with that of the curve at that point. The radius of that circle is marked by r, and the curvature is equal to 1 over r, the sign being plus or minus according to whether the curve is turning toward the oriented normal, in which case it's positive, or turning away, in which case it's negative. We can use the notion of the curvature of a plane curve to define the normal curvature of a surface. Consider the surface drawn on the left, and at a point on the surface, a normal plane P. This plane P slices the surface in a curve. That curve is a planar curve drawn on the right, and it has a planar curvature, which might be positive or negative. That planar curvature is said to be the normal curvature of the surface at that point in the tangential direction determined by the plane P. This is how we define normal curvature. And here we define the mean curvature and the Gauss curvature to be the average and the product respectively of the principal curvatures. Remember, the principal curvatures are the maximum and minimum of normal curvatures. For example, we can start out with a graph of a function. This will give us a surface. And we're going to make simple definitions of the Gauss curvature and the mean curvature by making a simplifying assumption at one point. We'll take the point 0, 0 in the plane and assume that the tangent plane there is horizontal. In other words, the first derivatives there vanish. Then the mean curvature is just half of the Laplacian, and the Gauss curvature is exactly the determinant of the Hessian. In general, the mean curvature is given by half of this quotient, and as can be seen, for example, for constant mean curvature, we have a nonlinear elliptic equation. The surfaces we're interested in are called minimal surfaces, and they're defined by the variational equation mean curvature is exactly equal to 0. Now, let's think what this means for a second geometrically. It means that the principal curvatures, the maximum and minimum of normal curvatures, are exactly equal and oppositely balanced. So the surface is in equilibrium locally. From a global point of view, you're looking at surfaces which locally minimize the area integrand. One simple but important way to realize minimal surfaces is as solutions of a boundary value problem. We can take a boundary in space and try to find a surface of minimum area spanning it. And this can be modeled by using soap films. Okay. Here we have a soap film bounded by 4 straight lines. The bottom one is free to move. Now watch what happens when I tip it up. Before I get to horizontal, the bottom bar is going to be pulled up by the surface tension exerted on the bar by the soap film. What do we see here? We see that the surface made up of a soap film actually exerts force on the boundary. And it is trying to reduce its total tension, and by doing so, reduces its area. When the boundary was free to move, the surface shrunk up until it actually disappears. It can be shown mathematically quite easily that trying to reduce total surface tension will produce a surface that also tries to minimize area. So we can model surfaces of minimum area by soap films, which try to reduce their total surface tension. Because we're going to be concerned with surfaces of infinite extent and infinite area, it is important to emphasize that the definition of minimal surface does not mean that a surface has finite area. It just means that it's locally area minimizing. Let me try to explain that by using two things. First of all, the surface behind me, Costa surface, about which more later, and second, a model of it made out of clay. I'm going to try to explain to you the sculptor's definition of a minimal surface. A surface is minimal if it meets the following criterion. Take a small piece of it, cut it out, and save the piece. Then make a wire boundary exactly equal to the boundary of the hole that you cut out. Now use that wire boundary to form a soap film, in other words, an area minimizing surface. Make sure that the piece you cut out matches exactly the soap film. In other words, make sure that the surface is locally area minimizing. If you can do this everywhere on the surface, then the surface you have is a minimal surface. While minimal surfaces are defined in a very geometric fashion, they have many wonderful analytic properties which enable us to investigate them using tools of calculus. One of them is that the coordinate functions on the surface are harmonic functions. And this leads to a very important property of minimal surfaces known as the flux formula. Let me try to explain that to you in terms of the following diagram. Take a surface that's supposed to be a minimal surface, which is compact. It has some boundary. And consider along the boundary the outward pointing conormal vector. In other words, this would be your velocity vector if you were moving along the surface and left it orthogonally at unit speed. This is indicated by n star. It turns out that the integral along the boundary of this vector is equal to 0 on a minimal surface when integrated with respect to arc length. We can use this flux formula to derive the equation of a minimal surface of rotation known as the catenoid. Consider a surface of rotation generated by a curve r of t. Now, at any given height, t, the radius of the circle on this surface is r of t. And the outward pointing normal is just computed by r and the derivative of r. Because the flux in any circle must be equal to the flux on any other circle, one derives a differential equation by integrating and gets the 2 pi r times the cosine of alpha is equal to a constant. Alpha is the angle of the normal n star with the vertical. Converting cosine alpha into an equation involving r and r prime, one gets the equation of cosh. In other words, r of t is given by this formula involving cosh. Now the constant b is just a vertical translation parameter. If you increase b, the catenoid will move up. And the constant a is a scaling parameter. In other words, changing a changes the scale of R3 in which you view this surface. So, up to translation and scaling, there is only one minimal surface of rotation, the catenoid. Now we'll see some pictures of it. Here is a picture of the catenoid. I'd like to point out some properties of it that are quite important for a future discussion. First of all, you only see a compact piece of it. It extends forever. Second of all, the generating curve is the cosh, which means that as a graph over, let's say, the horizontal xy plane, you will see any generating curve growing logarithmically. This property is something that will be shared by all minimal surfaces of a certain type that are embedded. But I think it's important before we proceed to see what the catenoid looks like in a much larger piece from much farther away. Here it is. You can see that it gets very, very flat, and it looks like a mattress button. In fact, because it grows logarithmically, it is ultimately below any linear function. We are interested in minimal surfaces that are embedded, properly embedded, that is, and complete. In other words, these surfaces could be considered the boundary of solid, smooth domains in space. We want them also to have one of two properties. The first of which is topological finiteness. That is, the surface is homeomorphic to a surface of genus K, K finite, and has R ends, R again finite. In other words, the surface should look something like this. As it goes off the page, it might be imagined to go out to infinity like a plane or like a catenoid. but even off the page it does not intersect with itself. Well, examples are the flat plane, the catenoid, which we've seen before, and the helicoid. The helicoid is a surface that is actually generated by a one-parameter family of straight lines, and it can be shown that it is the only ruled minimal surface, even locally. Now, this surface has genus 0. It's topologically the plane, and it has one end, therefore. It is also singly periodic, as can be glimpsed or guessed from this picture. Let me show you a somewhat more complicated singly periodic surface. This is Schwarz surface. One can imagine this as the intersection of two orthogonal planes with the line of intersection removed and replaced by a sequence of tunnels. Now, the helicoid is a topologically finite surface, and it is also a singly periodic surface. And therefore, it is an example of both of the sorts of surface we're interested in, either topologically finite or periodic. That's the second criteria. This surface, Schwarz surface, is singly periodic. It has one translational period, and it is topologically infinite. Let me show you a doubly periodic surface also found by Schwarz in the next picture. This surface can be conceived of as a family of half planes meeting another family of half planes that have been rotated by 90 degrees and matching up by an infinite number of saddle surfaces, small saddle surfaces. Now, as an example of a triply periodic surface, I want to show you a recently discovered one, which we've been able to reconstruct and animate. This one was recently discovered by German crystallographers by the name of Fischer and Koch. As you can see, it's built up out of a relatively simple piece, but when it's full-blown, it's quite complicated looking, and it consists of, one might say, the desingularization of a family of planes meeting at 60-degree angles. Let's discuss in a little more detail how one would construct such surfaces. In order to do this, we have to consider what's called the Plateau Problem. The Plateau Problem is named after a Belgian physicist of the last century by the name of Joseph Plateau, who posed the question to mathematicians coming from problems in surface physics. So the question is this: given a closed contour in space, perhaps one curve, perhaps many curves, does there exist a minimal surface with that contour as boundary? If there exists one, is it unique? And how can you describe it explicitly? Now, we can actually model a plateau solution by a soap film experiment. In other words, we can find an area minimizing surface physically by getting a soap film to span a given contour. I should say that for simple closed contours, it is always the case that there is an area minimizing surface with that contour as boundary. I'm now going to do an experiment with two contours for which this is not always the case. Now, I'm dipping it in a soap solution, and you'll see I have two rectangles as my boundary. I'm going to try, again, to create a surface that's topologically annulus with these things as boundary. I do that by sticking something through in the middle. There we have it. I hope you can see that. Now, as I move around, you see I solve the problem continuously with this physical model. But watch what happens when I try to move one too high up. It pops and forms two planes. In other words, I get two separate solutions. It's not the case that given two separate simple closed contours, one can find a connected minimal surface spanning them. In other words, a connected surface whose boundary consists of precisely these contours. If they are too far apart, such an area minimizing surface does not exist. There may be unstable surfaces, there may be no surfaces whatsoever. However, for simple closed contours, one can always assert mathematically the existence of a minimal surface with that contour as boundary. Of course, the plateau problem is a mathematical problem. In other words, we must prove the existence of a minimal surface with a given contour as boundary. The existence of a soap film is only suggestive. But let's presume that we can do this, and in a large variety of cases one can show that this does exist. How can we continue this to a natural example, in other words, to a periodic embedded minimal surface? The method we'll use is called Schwarz Reflection. This comes from the Schwarz Reflection principle in complex analysis. As we'll see later, minimal surfaces are intimately connected with complex variables. This principle has two parts, the first of which says that if you have a minimal surface that has a line on its boundary, you can rotate the minimal surface about that line and extend the minimal surface to a new minimal surface that's larger and contains a line in the boundary. A companion reflection principle says that if you have a minimal surface which meets a plane orthogonally, then you can reflect that minimal surface through the plane, and again you get a larger minimal surface that's smooth across the plane. Now let's see how we can use this to construct minimal surfaces that are embedded and periodic. For example, we can start out with a contour like this that consists of two right angles joined by small verticals here which are denoted in green. One has to imagine a minimal surface with this boundary, and then the right angles getting longer and longer, the green verticals going out to infinity. Then one gets, and one can show that such a surface exists and is in fact a graph over an appropriate plane, one gets a minimal surface that can be extended by Schwarz reflection, that is by rotation about the lines on the boundary. Here we see it built up into some pieces, and this surface, if you look at it closely, and if I were to draw it a little better, you would recognize it as Schur's singly periodic surface. Here's a somewhat clearer picture of it. You might have to look a little to see the lines on it, but you can actually produce this surface, which we saw before, seems to be a desingularization of two orthogonal planes. Let's do something a little more complicated now. Let's take an angle as before, but this time not pi over 2, but let's say pi over 3. And again, solve the plateau problem. Let the vertical boundaries get farther and farther away. In other words, let the angles get longer and longer and longer. And in the limit, we get a surface that is again a graph, which if we reflect it about the boundaries can be continued to form this periodic surface discovered by Hermann Karcher some 7 years ago. Let's try something even a little more complicated. Let's rotate the top angle a little. So these lines now connecting the top angle to the bottom angle are not vertical. And as you extend the angles farther and farther out, these green lines will get longer and longer. One should stare at this for a minute and think or try to imagine what happens when you extend this by Schwarz reflection. In other words, reflecting about the lines on the boundary. What you get is this surface, which is a surface discovered by Pitts and Karcher at about the same time as the previous surface. Now this is a little strange. It's hard to imagine what the surface really looks like. One could think of it as going out to infinity like a helicoid. In fact, one could imagine this as three helicoids intersecting, and the intersection being desingularized. In any case, it is constructed by use of the Plateau Problem and Schwarz Reflection. Let's take another variant on the boundary, and let's look at the Fischer-Koch triply periodic surface again. Here is that very piece illustrated on the left. Karcher and I then thought that the horizontals could be extended out to infinity. It's very simple to prove that you do get a plateau solution that converges to an infinite surface. And this surface can again be continued now to a singly periodic surface, which I'd like to show you in an animation. Here we see the plateau solution with this particular boundary. And one has to imagine that these edges, this one and that one, are extended off out to infinity. In other words, we take a sequence of plateau solutions that in the limit will give a surface that looks asymptotically like two flat strips. Now we're going to move this around. It makes it a little easier to see and bring it back into a symmetric position in order to reflect it first around the little short lines and get a doubled piece. Now this doesn't look too complicated now, but watch what happens when we do the next reflection. The next reflection will be around one of the longer lines. Okay, we're going to speed up this animation to the next reflection, which is coming around here. And notice, slowing it down, that this begins to look like the intersection of three planes. In fact, it is exactly that. We will have an embedded surface, which is asymptotically three planes intersecting at equal angles, and also contains a vertical line down the axis. What we've just seen is a singly periodic surface generated by a plateau solution, as we see here, where the angle is 60 degrees. In general, one can do this for any angle, pi over an odd number. For example, for pi over 5, we can generate a surface that looks like this. Another thing one can do is analogous to the example of Karcher and Pitts. Namely, one can rotate the top angle by a small amount. And in fact, one produces a surface that looks like this. It goes out to infinity like three helicoids. In fact, these surfaces exist in a one-parameter family. One can imagine taking this angle, which here is illustrated as 0, and making it grow through epsilon, and epsilon increasing. So we can generate a one-parameter family of embedded minimal surfaces that are singly periodic, that go out to infinity like helicoids, or like a bunch of helicoids, and we get actually a smooth deformation family of them, as we'll see in the next video. There's a second way to construct minimal surfaces that is more general than the Plateau solution. This is the so-called Weierstrass-Enneper Representation, which takes advantage of the deep connection between the theory of complex variables and minimal surface theory. I'd like to illustrate that by working with one specific example, the catenoid, which you see here. Recall that the catenoid is a twice-punctured sphere. That is, it's genus 0 and it has two topological ends. Its total curvature is minus 4 pi, a consequence of the fact that its Gauss map is 1-to-1 onto the sphere minus 2 points. Let's take a look at that schematically and say specifically what the Gauss map is. At each point on a smooth oriented surface, one can define a map taking the surface into the unit sphere by taking a point on the surface into its unit normal. We can then compose that map, G, with sigma stereographic projection onto the plane and produce a map from the surface onto the complex plane. Now, in terms of the catenoid, one can see readily that the Gauss map is one-to-one onto the sphere, except one misses precisely 2 points, which turn out to be, after stereographic projection, the origin and the point at infinity. These correspond to the North Pole and the South Pole. Therefore, we can parameterize the catenoid by the complex plane minus the origin. And in fact, we can recover the catenoid in space by the formula you see. This formula involves complex contour integration in the plane, and it involves the Gauss map in an essential way. You see here the red z squared, and you see here the red z itself in the third integrand. It is a fact that on a minimal surface, the Gauss map is conformal and can be used to represent the surface. Let me say that specifically by taking a look at the next picture. Consider a surface in space M immersed by a mapping X from some abstract surface. Its Gauss map is indicated by capital G, and little g is stereographic projection of the Gauss map. For a minimal surface, little g is always holomorphic. And in fact, one can recreate this immersion, in fact a conformal immersion, by the following formula. So one starts out with a Riemann surface, a surface endowed with a conformal structure, a meromorphic function on the surface, and a one form on the surface. And one forms these contour integrals and takes the real part, and that reproduces the minimal surface in space as a conformal immersion. Now, one has to have a matching between this one form eta and the Gauss map G in order to make sure that there aren't singularities on the surface, places where the surface is weakly conformal. And properties of the surface, geometric properties of the surface, can be read off from properties of G and eta. To illustrate how this works, we're going to show you a computer graphic computation of Enneper surface. This is a surface that's defined on the complex plane, where the Gauss map G is exactly Z, and the one form is dz. In fact, you're going to see an illustrative use of a program called Mesh, written by Jim Hoffman, which is used to create almost all of the computer graphics seen in this film. What you're going to see here is a representation of the complex plane, and some points have already been computed on the surface. And now I will step back so you can see those points in space under the Weierstrass-Enneper map. And now we're going to let the computer run, and you'll see more and more points being computed and the surface rotated in space. This program Mesh tries to lay out the points so that the triangles are approximately equal in area, and so that the curvature, the total curvature of each triangle, is not too big. What you see here is a piece of Enneper surface which actually extends out to infinity. Here it is filled in by the computer with a simple color map. You can see that the surface self-intersects. So this is not a natural example. This is an example that is topologically finite. It has genus 0 in one end, but it self-intersects. We've seen two examples, the catenoid and Enneper surface, both of which have been constructed using the Weierstrass-Enneper representation with the Gauss map equal to Z. In fact, on a minimal surface, away from points where the curvature is equal to 0, those are points where the Gauss map is singular, you can locally parameterize the surface by Z, namely the local uniformizing parameter on the sphere. So that's not a surprise. In fact, we're going to construct some very complicated surfaces now whose Gauss map is given by Z in some sense. Here's Shirk's singly periodic surface. What is the underlying domain? It's the complex plane minus the fourth roots of unity. The Gauss map is again Z, and the one form is Z to the fourth minus 1 inverse times dz. I've drawn a piece of Shirk's surface parameterized by the unit disk. The surface is bounded above by two somewhat parabolic arcs, actually they're more hyperbolic than parabolic, which meet a horizontal plane orthogonally. And the same thing happens on the bottom. there are two straight lines on the surface. These correspond to the red lines you see in the diagram. However, if you look at the four roots of unity, you see four small green circles, and these correspond to the vertical edges. As you go to these points, the surface goes out to infinity. It does not stop there. And as you go around, you actually pick up a period. Remember, the Weierstrass-Enneper representation is defined in terms of a complex contour integral. And at these points at infinity, namely the fourth roots of unity, you pick up a period. So in fact, this surface extends. As you go around those points, you get a multi-valued map from the Weierstrass-Enneper representation. We can see the surface if you pick up several pieces, namely going out to infinity and coming back again by going around one of those points in the following slide. It is Schur's surface again. Now we're going to make a slight change by multiplying the one form eta by I. Nothing else has changed, and yet the geometry changes radically. The curves which were these planar geodesics, these curves in horizontal planes of reflection on the surface, now become straight vertical lines. The curves that were previously straight lines become reflectional lines of symmetry that go through the saddle point. And in this case, one has not one vertical period, as in the previous case, but two horizontal periods. These two periods are orthogonal to each other, and on the ends corresponding to the points on the real axis, they are the same. On the ends corresponding to the points on the imaginary axis, they are the same. So one will get, via this construction, a multi-valued map that actually gives you a doubly periodic surface. Alternatively, you could construct the surface by rotation about the vertical lines. And here's a picture of it. It is again Schur's doubly periodic surface. This is a surface of infinite genus, and yet it was defined by the Weierstrass-Enneper representation on a domain consisting of the sphere minus 4 points. What is going on? In fact, let me repeat that the Weierstrass-Enneper mapping had periods, so it actually gives you a multi-valued map. And so we get a larger surface, still embedded, still interesting, but not one of finite topological type. In order to get a surface of finite topological type from the Weierstrass-Enneper representation, one must construct the data, the one form in the Gauss map, to have no periods. So, how can one solve this period problem? In other words, how can one construct minimal surfaces that are properly embedded in a finite topological type? Let's look at the known examples that are classical examples. First of all, of course, is the flat plane, a very simple minimal surface whose Gauss map is constant. It has genus 0 and one end. Then there's the catenoid, which we've seen before, genus 0 and two ends. And finally, the helicoid, which is genus 0 and one end. Let's take a look at the helicoid now. Here is the helicoid. We've seen it before, and we know it's a surface of genus 0 with one topological end. It's a periodic surface that isn't flat, and that means it has infinite total curvature. It is also properly embedded. It's a surprising and somewhat annoying fact that even though the surface has been known for 200 years, it is the only known example today of a properly embedded minimal surface of infinite total curvature and finite topological type. Recently, Bill Meeks and I have been able to prove that if you have a properly embedded minimal surface, then at most two of the ends can have infinite total curvature if the ends are topologically annuli. Here is one end that's topologically annular and it's embedded. It might be the only such end of infinite total curvature. This is still an open question. In the case of finite total curvature, the situation is quite different. And one can hope to construct examples, and one can concede in constructing examples, by using a result of Osterman, which says, roughly, that finite total curvature implies finite topology. More specifically, Osterman was able to show that if you have a complete minimal surface of finite total curvature, then conformally, it is a compact Riemann surface of finite genus, punctured in a finite number of points, and the Gauss map which is meromorphic on the surface, actually extends to the compact surface as a meromorphic function. Therefore, one can hope to construct an example as follows. Start out with a compact Riemann surface, bold-faced M, and puncture it at a finite number of points, P1 through PR. Specify a meromorphic function G defined on the compact surface, and a compatible one form, whose details I won't go into, to make the surface regular and complete. Also, specify that G has poles or zeros at the punctures. This will mean that as you go to infinity, the limiting normals at infinity will be parallel, and the surface has a chance of not intersecting itself at infinity. Then, one has to solve the period problem. In other words, one has to make sure that this map is really well defined on the surface. What does that mean? On every closed path on the surface, one must have that as you circulate around the closed path, the Weierstrass-Enneper mapping gives you the same point when you come back to the original starting point. In other words, as you go around the path, all of these integrands have zero real period. If you succeed in doing this, then you have a well-defined finite total curvature surface that might be well-behaved at infinity, but you still don't know whether it's embedded. The first real breakthrough in this problem was made by Costa. He was able to define on a rectangular torus a Gauss map in a one form that would produce a surface of genus 1 necessarily with three topological ends, the top one and the bottom one asymptotic to catenoids, and the middle one asymptotic to a plane, which was embedded at infinity. So he was able to solve the period problem, but not able to show that the surface you see here was embedded. Let's take a closer look at this surface. It is hard to see here that it has lines on it, so let's first start with the fact that there are two obvious vertical planes of reflectional symmetry. Now, through the saddle point there are lines that meet these planes of reflectional symmetry at 45-degree angles. Those are hard to see here, but you can imagine the surface twisting around those lines and going into itself. So there is a horizontal line going through the saddle around which the surface rotates into itself. Perhaps this is a little too hard to see, so let's look at an animation of this surface. Look at a rotation of it made several years ago by Jim Hoffman. Costa was able to prove that this surface existed, namely it was a finite total curvature surface of genus 1 with three ends that was embedded outside of a large compact set. With the help of Jim Hoffman's graphics, Meeks and I analyzed the structure of this surface and showed that it had a lot of symmetry. And using that symmetry, we were able to show it was embedded. Going further with the symmetry, we were able to generalize the construction from tori to hyperelliptic Riemann surfaces and show that for every genus greater than 1, there was an embedded example with three ends. Let's take a look at them. Here is the Costa example. As you can see, it has two vertical planes of symmetry, and as you can imagine, it's a little hard to see, there are two lines crossing at right angles at the saddle diverging into the pink flat end. Now I'm going to increase the genus by 1 and show you the genus 2 example, on which there are three lines diverging into the flat end and three vertical planes of symmetry. And now I'm going to increase the genus by one more again, and you see that more and more holes are hanging out around the origin, and the surface is looking more and more like a catenoid up and a catenoid down. We increase the genus more, and you see that the structure becomes more and more pronounced. You can almost imagine what's going to happen in the next slide and in the next one. Now, here one could begin to ask the question, what happens in the limit? And there are two ways to make sense of that. First of all, let's imagine that the tunnels, while increasing in number as the genus goes up, stay bounded, and they stay nested around a circle of radius 1, that circle being between the two top and bottom catenoid ends, passing through the planar end. Then we were able to show that in the limit, the sequence of surfaces converges to the plane union the catenoid. It converges smoothly away from the circle of intersection. If, however, you went back to the surface and refused to let that happen, because when that happens, the curvature blows up in those holes. If you normalize the curvature so that it was never bigger than 1 in absolute value, then you would force that ring of holes to expand out, and we were able to show that in that situation, when you went to the limit, you got this familiar surface, namely Shirk's singly periodic surface. Here again we have a picture of the original Costa surface. Meeks and I were able to prove that this surface, as well as all its generalizations which you've just seen, can be deformed through a one-parameter family of embedded minimal surfaces. And as the deformation begins, the flat planar end in the middle deforms and becomes catenoidal, just like the ends on top and bottom. To show you this in an animation, we're going to have to, because of the way it was rendered, rotate this surface so it is lying horizontally. Here's the surface rotated, and now we're going to see the one-parameter family of deformations. As you can see, it really looks like it's made out of a soap film that's gradually expanding and is about to pop. The marks you see on it are computational errors having to do with the fact that we computed only a part of the surface and reflected it to get the other half. In fact, it's possible to use the idea behind constructing the Costa surface to make even more complicated surfaces. Let me describe intuitively how one could imagine doing that. Look behind me at the top half of the Costa surface and imagine instead of it diverging asymptotically to a catenoid, you were to cut it off and deform it slightly so that the circle on which you cut it off, or rather the closed curve on which you cut it off, met a plane orthogonally. Then you could reflect it, and you would form a surface that would have 2 flat ends. The genus would double, it would be genus 2, and it would have a catenoid end top and bottom. In fact, by using this idea and analyzing what the Weierstrass-Enneper representation would have to be, Michael Callahan, Bill Meeks, and I were able to do just that and show that for every even genus, one could construct an embedded example with 4 ends. And to prove this, we had to go a little bit beyond what happened with the examples generalizing the Costa examples. We had to give a proof of embeddedness as well as a proof of existence that involved a degree theory argument, and that argument was bolstered by computer computations. Let's take a look at that surface. The surface has been rotated because the images were rendered this way, but you can see that to my right, there's a surface that looks like Costa surface that doesn't diverge too much. It then becomes flat in the middle here, reflects through a plane of symmetry here, and produces a genus 2 surface with 2 flat ends and 2 catenoidal ends. Now we're going to show you an animation of this surface that will, I believe, reveal its properties a little more clearly. Here we see half of the genus 4 surface. As you can see, one could imagine that this is the genus 2 surface with 3 ends, cut off so that one of the catenoid ends is squashed down and deformed so as to form a curve that you see in the center of your screen lying on a plane, and done so that the surface meets that plane orthogonally. Therefore, we can continue it by Schwarz reflection and form a surface with 4 ends of genus 4. We're going to see this happen by the level curves being drawn slowly in the following animation. At this point, we have the second flat end, and the surface is now diverging to the far right-hand side catenoid end. We'll stop for a second and then move it backward so you can get another view of how the surface is constructed by level curves. Here we have again the genus 4 surface with 4 ends that we just saw in the animation. And now we'd like to try to imagine making it even more complicated by drilling a hole right here. Now to do that, one would have to change the Weierstrass-Enneper representation. It would become more complicated. It would be defined on a more complicated higher genus Riemann surface. This is actually possible to do. And in order to illustrate it, let's go back and look at the 4-ended surface of genus 2 that's a little simpler than this. Here we can imagine drilling a hole right here in the center. It's hard to find the center. There it is. Okay. In order to illustrate that that happens, let's look at the next slide. There it is. It's a little hard to see the hole, which is right here. Now, these surfaces were discovered by Meinhard Wohlgemuth, who actually showed that this was possible, but the proof still involves doing a computation for each genus. In order to illustrate what's actually going on here, let's slice the surface by one of its planes of symmetry so we can actually see the hole. There it is, sliced by a vertical plane, and you can actually see where the hole is right there. Now let's go back to the whole surface and slice it by a horizontal plane of symmetry. And you can see again the hole even more clearly here. In fact, Wohlgemuth was able to show that for each genus 3K, one could construct a surface like this with 4 ends, 2 flat and 2 catenoidal. Very recently, he's been able to show that it's possible to wiggle those ends. In other words, to deform these 2 middle flat ends a little bit to make them catenoidal. And this raises a question, well, how much more can you do and how much more do you really want to do computationally? In other words, is it possible to describe in an analytic or algebraic way the structure of the space of all embedded minimal surfaces that are complete and have finite total curvature? Before leaving these examples, I think it's important to take a look at this example of Wohlgemuth, which is a surface of genus 9, again with 4 topological ends. One sees more and more handles popping up in the middle here. So one can add more and more handles, but perhaps not more and more ends. This surface is sufficiently complicated to make one pause about constructing new examples and to start to think, as I said before, about what the structure is of the space of possible examples. One could begin by asking, what are the obstructions to constructing examples? And at the moment, there are only 3 known. Let me describe them briefly. One is a result of Rick-Shane that says if you have a finite total curvature complete embedded minimal surface that has 2 ends, then regardless of the genus, it in fact has genus 0 and is the catenoid. A more recent result of Lopez and Ross says that if you have such an example of genus 0, then it is in fact the flat plane or it is the catenoid. And finally, Costa has recently proved that his surface plus the deformations we saw earlier are the only 3-ended embedded examples of genus 1. Except for these results, not much more is known. We've seen from the examples that if you fix the number of ends greater than 3, you can increase the genus without bounds. However, it's probably not the case that you can reverse the order. If you look at this theorem of Lopez and Ross, it says that when the genus is 0, you can only have 1 end and have the plane, or 2 ends and have the catenoid. It's probably true that if you fix the genus at k, then there is an upper bound for the number of ends, r, probably k plus 2. This is an open problem. The only other result that I know at the moment is something that Meeks and I were able to prove, which goes as follows. If you have the space of complete embedded minimal surfaces of finite total curvature, whose genus is less than a fixed number k, and whose number of ends is less than a fixed number r, then that space, if normalized so that the maximum curvature is equal to 1 in absolute value and occurs at the origin, a natural normalization, normalizing by translation and homothety, then that space is compact. In other words, one can take limits in that space, which means that sequences that degenerate must degenerate by losing ends or losing genus. In order to talk about the connection between surfaces that minimize area and polymer physics, we're actually going to have to talk about a slightly more general class of surfaces, namely those with constant mean curvature, not necessarily equal to 0. Let me try to explain what that means by thinking of what a minimal surface would be if it wasn't a surface at all, it was a curve in the plane. Recall that a minimal surface is one that is locally area minimizing. Therefore, if we wanted to look at the analog of a minimal surface that was actually a curve in the plane, we'd want to look at curves in the plane that were length minimizing, at least locally. Well, it turns out that this means you would have a straight line in the plane. These are precisely the curves in the plane that are length minimizing, locally or globally. And such a curve would have 0 curvature. Now, the curves with constant curvature in the plane are precisely the circles. And let me now do an experiment analogous to one we had earlier. Here we have an apparatus that consists of 2 straight lines forming an angle and a thread that is free except at its endpoints. Now what do we expect when we dip this into a solution which forms a soap film with these boundaries? We're going to see something that is planar with a thread forming a boundary curve, a plane curve. What will it be? Let's do it. In minimizing surface area, the thread of fixed length is pulled by the film into an almost perfect circle. One can extrapolate from this experiment the following true mathematical statement. Among curves in the plane of fixed length, the circle bounds a region of least possible area. In fact, the dual statement is also true, namely this. Given a simply connected region in the plane of fixed area, the one whose boundary is shortest is always a disk. The boundary of the disk is a circle, a curve of constant curvature. Now, if we consider back in the realm of surfaces in 3-space, a surface which encloses a fixed volume and tries to minimize its surface area, the solution to that problem is well known to be a round sphere, and we can do a famous soap bubble experiment to show that this is in fact what you see. You blow a bubble, as you will see, and what happens is that you enclose a fixed amount of air. Now, the soap bubble tries to minimize its surface area, but it encloses a fixed amount of air. That air cannot go anywhere. So what it is trying to do after it compresses the air to a certain fixed volume that will not change, will not get any smaller, is try to minimize its tension or its surface area subject to the constraint of enclosing a fixed volume. And one gets a surface of constant mean curvature. So, if one looks at the variational problem of minimizing area subject to the constraint of enclosing a fixed volume, the variational equation tells you that at each point the mean curvature is equal to a non-zero constant. In other words, we're looking at surfaces of constant mean curvature. In this case, that constant is not equal to 0. Now, we might want to ask what the analog is of the catenoid. In other words, what are the surfaces of constant mean curvature, which are surfaces of revolution? And here, again, we must say that we're going from the local variational condition of constant mean curvature to a surface, because some of these surfaces we will see do not enclose a finite volume. For example, one can have spheres, as we've seen, but also cylinders, and other surfaces of revolution that were first written down by Delaunay in the 19th century. In fact, there's a one-parameter family of periodic surfaces of constant mean curvature that are topologically a cylinder that degenerate into a sequence of spheres. And we're going to see this in an animation that shows sections of the Delaunay surfaces of revolution with constant non-zero mean curvature. Here we see half of a Delaunay surface of revolution slightly perturbed from a cylinder. Now we're going to start the animation and watch it deform through embedded surfaces until we stop it just at the point where it becomes singular. Now, at this point, what we're looking at is a sequence of spheres that touch each adjacent sphere at one point. After this, the family actually continues through surfaces that are not embedded. These are the so-called nodoids. The earlier ones, the embedded ones on the other side of the sphere, are called unguloids. The surfaces of revolution with constant mean curvature that we've just seen are all non-compact with the exception of the sphere. The sphere is a surface of revolution and also a surface of constant mean curvature. For a long time, it was the only compact surface of constant mean curvature without boundary that was known. In fact, it was suspected that this was the only closed compact surface of constant mean curvature. It was proved by Hans Hopf that if you had a surface of genus 0 that was compact and closed, it had to be the sphere. Alexandrov proved that if you had a surface that was embedded, compact, closed, with constant mean curvature, it had to be the sphere. And it was conjectured that the sphere was the only closed surface of constant mean curvature. This was a so-called Hopf conjecture. It turns out that this is not true. In fact, it was proved by Wente in 1984 that there were infinitely many genus 1 surfaces that were closed and had constant non-zero mean curvature. These surfaces were not embedded, of course, and were somewhat complicated. We will now show you some pictures and animations made of this surface based on work of Albrecht, who reduced the solution to this problem to solving certain ordinary differential equations. I should also mention before we look at these pictures that Capillas has constructed by very complicated methods compact surfaces of genus greater than 2 of constant non-zero mean curvature and embedded complete non-compact surfaces that are asymptotic whenever they go to infinity to the Delaunay surfaces we've just seen. Now let's take a look at one of the Wente surfaces, the so-called 5-lobed symmetric Wente surface. Here it is cut in half. This surface closes up by reflection through the plane which you see in the front of the screen. You can see it's highly symmetric and also full of self-intersections. To get a better idea of what this looks like, we're going to show you an animation of this surface completely closed up, all the interesting geometries on the inside, and then we will slowly make translucent the front half of the surface. In other words, you will see the part of the surface that's cut away and invisible here at first there and then disappear. Then we will run it backwards so you can see the surface close up again. Here it is, the full compact 5-lobed Wente torus of constant mean curvature. It's a genus 1 surface. And now we're going to start the animation during which the front half of it will slowly become translucent and we can see the inner geometry. Now we're going to run that backwards and slowly close up the surface, making it more and more opaque, and end up at the view from the outside of the surface. Now, there are doubly periodic surfaces of constant mean curvature that were recently discovered, and also triply periodic ones. It's quite surprising to realize that even though this was a clear subject of investigation, it was only in the latter half of the 20th century that people paid serious attention to these surfaces. And part of the motivation for doing so was that they seem to arise naturally in the subject of polymer physics as interfaces between compound polymers. We're going to see a picture of a surface discovered by David Anderson, a triply periodic surface of constant mean curvature, one of a family of surfaces with diamond symmetry. What we're seeing here is a surface discovered by David Anderson in the mid-80s. It's a periodic surface, triply periodic, with constant non-zero mean curvature. In fact, this image was simulated on the Cray at Minnesota, and these surfaces were discovered by Anderson at first computationally. Later, they were proved to exist theoretically. Now, Anderson was not a mathematician, is not a mathematician. He's a polymer physicist, and he was interested in the surface as an interface between compound block copolymers and also liquid-liquid mixtures. This is a schematic of a basic piece of the Anderson triply periodic surface. And let's look at it and try to imagine that the dark substance inside the surface is one long molecule, one polymer, and the exterior, the white substance, the matrix, is another polymer. For example, this could be polystyrene polyisoprene, and we can imagine that it's a block copolymer. In other words, these two long molecules are bonded together in some configuration. Now, they naturally like to repel each other, but they're bonded together, so they cannot be any huge distance apart. They can only separate in a certain way. I'm actually going to present to you some experimental results of Thomas and Anderson and others at the University of Massachusetts and the University of Minnesota that indicate that, in fact, in certain copolymer blends, one is going to see an interface between one substance, one polymer, and the other that is a surface of constant mean curvature that is very close to or identical to the surface that you're seeing here. So what happens? These substances cannot be compressed too much, and they cannot get too far away. they're going to form an interface. And that's the interface which we try to model as a surface of constant mean curvature. In other words, we're trying to make the argument that the interface is trying to minimize its surface area. At least this is the first order of whatever functional it is trying to minimize, whatever energy is trying to be minimized in the presence of a substance that won't go away. And so we're, roughly speaking, in the realm of constant mean curvature, minimize surface area, minimize surface tension, subject to a fixed volume constraint. In this next illustration, we see various configurations that have been observed and computed theoretically for the surface interface between one copolymer and another. And note that they are all surfaces of constant mean curvature. These occur as the volume fraction between one substance and the other changes. We begin on the left with small, light-colored spheres in a matrix of dark substance. This changes to a configuration of packed parallel cylinders, also surfaces of constant mean curvature, as the volume fraction changes. We then move to a situation where the double diamond configuration, the surface such as the surface of Anderson, a triply periodic constant mean curvature surface, is observed. And then we move to something that's roughly 50-50, where we have a constant mean curvature surface where the pressure from one side is roughly equal to the pressure from the other side, so to speak, and we get actually a minimal surface, a plane. And this is the case where one might get layers or lamellae. And then as the volume fraction keeps changing, we get the exact configuration, but with the substances reversed. Now, how would one determine the microstructure, the interface structure in a substance that is at once solid and which may or may not be periodic, but if it is periodic, it's periodic at a micro level? That is done in a variety of ways, one of which is a transmission electron microscope experiment using a thin slice of the material. Let me try to describe how that would go. First of all, one takes a thin slice of the material that might contain several periods of the conjectured structure. This is put under an electron microscope beam after one of the substances is doped to be somewhat opaque to the passage of electrons. A photographic film is then laid under the substance to register the beam, and one gets a grayscale image which is dark in the place where there's been a lot of occlusion of the electrons and light in the place where the electrons have passed quite freely. And by tilting the beam, one can get a sort of projective signature of the substance interface. Now, how can we determine what we are seeing? We can, on the computer, model the transmission electron microscope experiment by passing rays or tracing rays through a simulated substance whose interface is a numerically calculated surface that we guess is going to be the surface we see in reality, in the actual experiment. And then we can create on the computer screen a grayscale image that simulates what would happen if a perfect substance with exactly this constant mean curvature idealized interface were to be subjected to a perfect transmission electron microscope experiment. We also model in a little bit of the optics of the situation. Now one can make comparisons between the simulated projections, grayscale images, and the ones produced by the electron microscope. And here we see a series of them showing a pretty good match between the experiment and the simulation at angles that are previously determined to illustrate both the cubic structure of this particular triply periodic surface from one point of view and a diamond structure from another. We're now going to run through the simulation of the transmission electron microscope experiment with the Anderson surface. Here we can see the transition from a cubic symmetry axis to a diamond symmetry axis as indicated by these rotating hexagons. So what we've seen is a use of mathematics in applied physics. One doesn't want to prove mathematically that these surfaces are actually there. One has different goals that are not mathematical goals. But it must be said that research in this area has spurred research on the mathematical end to prove that these surfaces actually exist. And the existence of these surfaces has given to the physicists more models, more ways to recognize data that might have otherwise been thrown out or thought to be faulty or just misunderstood. And it should also be mentioned that the ability to model these surfaces on the computer, both to make pictures of them to make them be understood, and to model them numerically in order to conduct experiments on them, to mimic experiments done in the laboratory, is of great use. In my conversations with Thomas and Anderson and others, our common language usually starts out with pictures and sometimes goes beyond that, sometimes not. I would like to conclude with one other application of surface theory to the study of polymers, and that has to do with grain interfaces. What we see here in this sketch is a grain boundary formation. We're looking at a supposed polymer blend, let's say 50-50, which would naturally form lamellar sheets, where the interface is a minimal surface, a very simple one, planes. However, there's no reason for these planes to be oriented in a particular fashion. For example, on the left they might start out to be vertical plane interfaces, whereas on the right they might start out to be horizontal plane interfaces. And these substances might grow separately, and these grains might come into contact, and then we'd be faced with a situation of a family of parallel half-planes meeting up with another family of parallel half-planes at a boundary that's highly singular. What would happen there? Well, we've actually seen this a little earlier. We've seen a minimal surface, which asymptotically is a family of parallel half-planes meeting another family of parallel half-planes at right angles, namely Schur's doubly periodic surface. Here we see another image of Schur's doubly periodic surface. Locally, one might think of this surface as being built up of small saddles arranged over a checkerboard. But globally, again, let me emphasize that its structure is that of a family of parallel half-planes meeting another family of parallel half-planes that have been rotated by 90 degrees. The saddles may be thought of as the way these half-planes join up. In this image, we see two photographs. On top is a transmission electron microscope image made from a polystyrene polybutadiene block copolymer blend. This is made in a region where one would expect to see flat interfaces forming, lamellae. However, we're in a region where we have a grain boundary, and we see this sinusoidal pattern appearing. On the bottom is a simulation made on the computer of a transmission electron microscope experiment using as the interface Schur's doubly periodic surface. It's not an exact match, but it's fairly suggestive. I'd like to thank Ned Thomas, David Anderson, and Chris Henke for the preparation of the illustrative materials having to do with block copolymers and the transmission electron microscope slides. All the other graphics were made at Gang at the University of Massachusetts, and I'd like to thank my colleagues and collaborators who've worked with me over the years doing this research and preparing these interesting graphics. We've come to the end of our tour of these subjects. We've gone a little quickly and we've covered a lot of ground. I hope it's been of interest to you. Thank you very much.